Okay, and now I'm going to explain to you how to solve the question shown in the class slide last week with regards to Biot-Savart. So we have this triangle segment here. We want to find what is the magnetic field intensity produced at 005 caused by this segment, line 1. So in order to better visualize, we do a 3D drawing of the same triangle here to here. So we want to find what is the effect of this segment, what is the magnetic field is going to produce at this point, 005. Right, so this is another way of drawing it. We have two axes, X and Z, and the Y-axis is going into the page. So we see the segment 1 is this line here, and the point of analysis is this point here. Let's look at the equation that we want to use. The equation is this one. I already showed to you how we derive. The original equation is this one. So I already proven through the examples that from this equation here, we can derive to get this equation where we no longer need to integrate. So the solution becomes much simpler. So now we just need to find the values of R, theta 1, theta 2, and AV. Let's start with R. So R is the radius from the segment where we want to analyze to the point of analysis. So if we refer to the line here, this is the segment, and then when it carries current, it's going to produce a magnetic field around it. So the magnetic field will be circular in nature, and it goes bigger and bigger until it reaches the point of analysis. So we can say that the radius is equal to the length here, which is 5. So that is the value of R. Now let's look at cos theta 1 and cos theta 2. We know that cos is adjacent divided by hypotenuse. For theta 1, it's directly 90 degrees. Okay, how do we know? We know this by drawing a line connecting the point of analysis to the start point and from the point of analysis to the end point. So for the start point, we take the angle inside and we label it as theta 1. For the end point, we take the angle outside and we label it as theta 2. Now cos theta 1 is straightforward because it's 90 degrees. So cos 90 degrees is going to equal to 0. Meanwhile, for theta 2, we can find the angle inside here. The angle inside here, the cosine of the angle inside here is adjacent to divided by hypotenuse, square root 29. Because we already know the height here is 5 and the length here is 2, so we can find the hypotenuse. So cos theta here inside is 2 divided by square root 29. But because we want to find the angle outside, so we just need to apply negative. So we get cos theta 2 equals to negative 2 divided by square root 29. Right, now for the final part, we have AV. AV is equals to AL cross AR. So AL is the direction of the conductor. So the conductor is placed on the x-axis, so AX. While AR is the direction of the magnetic field to the point of analysis. So I showed just now, if the direction of magnetic field is going to be around here until it reaches this point. Okay. So actually the direction is moving upwards. We can take it as AZ. That's why we have here AX cross AZ. So the final direction or the result of the direction is negative AY. So finally we plug in into the equation. We have I equals to 10 amps, R equals to 5, 0 minus 2 divided by square root 29. So we get positive, then negative AY. So we get this value here, negative 1 divided by pi or times square root 29, or if we turn into decimal, we get negative 59.11 milliampere per meter. Okay, so sometimes in books, they can be using confusing symbols because this one is M, this one is also M. But the M here is milli and the M here is meter. So to be safe, maybe it's better to write it as times 10 to the power of minus 3. Okay. Personally, I prefer maintaining this format because it's a nice number rather than we turn into decimal point. Okay, that's it.